with one of the first publications of of theoretical papers proposing the transition of the maser, the microwave amplifier, coherent microwave amplifier that was developed by Towns and Sholov. The laser that first invention in 1960 was followed in 1960 by the invention of 5 or 6 additional lasers, and in 1961 by many other lasers, including the semiconductor laser and fiber laser and gas lasers. It was this 1960 really culminated in an explosion in the interest of lasers. And it's amazing how fast that concept spread around the world. I had the good fortune to work with one of the first professors in England who worked in lasers, Professor Daniel Bradley. I'm sure that some of my colleagues will remember Dr. Bradley. He became the leader in European laser physics for many years. Had a very large group, initially at the University of Belfast and then finally at the Imperial College in London. And I did my PhD. I was his first PhD student in lasers in 1964. And this is mainly simple flash lamp laser. This was my PhD thesis. It turned out to be the most powerful laser in England at the time. It was a Q-switch laser, had more than two laser cavities and many optics in it, including a Q-switch. Those of you who know anything about lasers know Q-switches. But the interesting part about this Q-switch was it was driven by a very high pressure, gas pressure system that sounded like a jet engine when it was turned on. And in fact, any scientist or any person working in the building, it was a very large 2-3-story building in a government laboratory. When my laser was turned on, everybody could hear it. Not many people could see it, of course, but they could all hear it. And that's probably the only claim to fame that I have in terms of my thesis. So from 1962 now to 2010, next year, as Dr. Paul mentioned, we will be celebrating the 50th anniversary of the demonstration of the laser, and we're all trying to create special events to celebrate this on the 16th of May for next year. So rather than look back on lasers of yesterday in any great detail, most of my talk will look forward now to where lasers are and where photonics is now, and where could it be, or where it is likely to be in the future. So you're going to hear some personal views here, or perspectives on the advances that have already been made and where they will be made in the future. We now can make lasers that are of extremely high power through various technologies. There's a technology called thin disk technology that is promoted by the German laser company Trump. It's used for many laser welding processes, and you can typically buy in our laser systems that have 16 kilowatts of light. The highest powered CW laser was demonstrated this past year by Northrop Grumman, over 100 kilowatts. 100 kilowatts is a rather magical number as far as high-power lasers are concerned, because this is really the threshold for many new defense applications of lasers. So we will see how these types of lasers get repackaged in the future to make complex, solid, rugged light machines or light engines of the future. You can already see some of those technologies emerging now. Fiber lasers that I will refer to more in the talk now are much more rugged than many of these types of multiple component laser systems. They fit in one box. They can produce they soon will be producing 20 to 30 kilowatts of power with very high efficiencies, wall plug efficiencies. To illustrate that point, there is a program just being funded now in the United States by DARPA. It's called the Rifle Program, but this is a program that will produce 3 kilowatt narrow line with fiber laser systems that will fit into a box, if I've got the box here, or that total weight of the system, including the power supply, has to be 5 kilograms. And the m squared is the value of the divergence. So once you get to m squared values close to 1, that's the minimum divergence that a light beam from a given aperture can have. So this is almost perfect laser divergence. You can see that these other laser systems have much higher divergence. There is obviously an advantage, especially an advantage for projecting light beams to large distances, to having minimum divergence. And you can obviously see the advantages of having laser systems that are of light weight, can be packaged small into rugged systems that could be carried on portable vehicles, for instance, for various applications, or remote systems. So what are the lasers going to be of the future? Well, here are a few ideas. Clearly, efficiency with lasers is going to be very important. And here it's a novel approach. It's not, at this point, demonstrated to be of high power. But clearly, as one builds laser systems, we all know that laser systems comprise of 3 things. An excitation source, a laser medium, and the laser medium is enclosed inside an optical cavity or an optical resonator. And as we drive these systems to higher powers and higher efficiencies, then
also on the editorial board, so several journalists, many of us are familiar with one of the editors of optics communication. He has been one of the pioneers in near field optics. This word has been mentioned in one of the slides of the picture. The inventor of heat enhanced near field microscopy, 3-dimensional microscopy, plasmonics, and multi-photon engineering and so on. He has authored more than 25 books, published more than 250 papers, and something interesting, which I am not very familiar what it means. His work 8 micron microbowl, which was made by 2-photon polymerization, his own invention, appears in Guinness World Book Record 2004 edition.